In this video, I'm going to look at how we can set up our groups as tables in order to do our binary operation. And then I'm going to use that with our model C3V symmetry group to show that it satisfies all of the things that make something a group, having a closed binary operation, being associative, having an identity element, and having inverses. And then I'm going to look very briefly at the idea of generators. And so what we have here are some multiplication tables, and so we could have a group like this that's just 1 and minus 1, and so we have a binary operation that's just multiplication. So you just take whatever is on top and multiply it by whatever is on the side here, and then you get this table that shows you all of the possible combinations. And so we could do the same thing with 1 minus 1, then I and minus I, where I and minus I are the imaginary numbers. And so I is equal to the square root of minus 1. And so you see if you take I times I, you get minus 1 because the square root of something times the square root of something is just whatever is the square root, whatever is under the radical there. But this, we could change the name of everything on here. So we change 1 to A, minus 1 to B, I to C, and minus I to D. And so what we actually have here is, and we'll look at this a little more in a future video, this is called an isomorphism. We're essentially just changing the names of everything, but the table ends up staying the same. So anywhere there's a minus I on here, so right there, right there, right there, and right there, you will find a D on this table. So we've just kind of changed the names of everything. All right, so if we want to look at our symmetry group, which was the C3V, which we were modeling by looking at these triangles, we can look at how this can be turned into a table like this. And so the binary operation that we're doing with this is essentially just doing one symmetry operation, then another one. And so, for instance, if you were going to do like the sigma 1 and then the C3, you would first do this one on this triangle right here, and then you do this one on whatever resulted from that. And we will look at that here in just a minute in a little more detail. But this is our table here, and so we have the things in this top row up here, and then you perform that onto the operations here in this column, and what you end up getting is, the things that are internal on this table. And so, for instance, if you did sigma 3 onto sigma 1, then you just go down here to where sigma 1 is in the sigma 3 column, and you see that that is the same as doing just a C3 bar. And so what we will see is that any combination of doing multiple of these symmetry transformations will result in just a single symmetry transformation. That has to do with the fact that the binary operation is closed. And so C3V has these as our elements. And so if we rearrange the elements, we will always get the same elements. And so what you see on here is that every row contains all of the elements once and only once, and every column contains every element once and only once. And so each row and each column is just sort of another rearrangement of each of these elements. And so when you rearrange them, you just get the same elements back out again. And each row and each column all contain every element, and they contain every element only once. And so that is the nature of our table for the group here. All right, and so then we can look at our C3V here, and we can see that first it has a binary operation, which, as I said, is just performing one of the symmetry operations or transformations, and then doing it again with the next one. And so, for instance, we have our binary operation here. And so, for instance, if we do our C3 first and then the sigma 1 second, and so you'll notice that you do that from right to left. And so the reason for that is because we want to think of this. So we have our sigma 1, then our C3, and you can almost think of that as like a function, and then we have our triangle here as like the argument of a function. And so you do this one first and then that one second. And so just like with when you're doing matrices, like when you're acting matrices onto vectors, you start from the right and sort of work your way left, and it will be the same for our symmetry operations here. And so we have our triangle here, and so if we first perform the C3 on it, which is a counterclockwise rotation, so a 120 degrees counterclockwise rotation, we get our triangle here. But now all of these points are going to be rotated once. So we have the 1 up here instead of right here. We now have the 2 down here and then the 3 here. Then we want to perform our sigma. I do that all the time, write them as an A. So we want to do our sigma here. And so the sigma 1 is reflecting across that that axis right there. So it's essentially just interchanging 1 and 2. So we end up with this. So 2, 1, and 3. But you'll notice, so if I put this here and just make the same one above it, so we have the 1 here, the 2 here, and the 3 here. If we do a sigma 2, then we are reflecting across that axis right there. And so what we end up with, we still have our 2 up here, but now we have a 3 here and a 1 here. And you'll notice that these are the same. And so that's what we mean when we set this equal to this sigma 2, is we're saying that doing those operations, doing those 2 operations is the same as doing this other operation just once. So doing the C3 and then the sigma 1 in a row is the same as just doing a sigma 2, and that is the idea that this is closed under our binary operation. So if you take any 2 of our symmetry operations and sort of compose them together and do each one in succession, you can always reduce that down to a single operation. And that's because one of the things about the closure in the binary operation is that you do the binary operation on any members of your group, and it will give you another member of your group. That's the definition of closure. And so we also have the associative property here. So we have the sigma 1, C3, sigma 2 on both sides, but we have moved the parentheses around here. And so what we end up getting, if we do the C3 sigma 2, is we end up getting a sigma 3. And so we can look over here at our table. So we have the C3, and then we use that on our sigma 2, and then come over here, that's a sigma 3. So we end up with that there. So a sigma 1 on our C3. So we have our sigma 1, then a C3 that gives us another sigma 3. So that ends up right there. And then so if we take sigma 1 and act it on sigma 3, so we take our sigma 1, act it on sigma 3, we get a C3. That's what we have here. If we take a sigma 3 and act it on our sigma 1, or on our sigma 2 rather, we get a C3. And so C3 equals C3. So that shows that it doesn't matter which of those 2 you put in the parentheses, you still end up getting the same thing. Don't mistake this for being commutative, though. So it is not the case that, like, say, if you did a C3, then a sigma 2, that would be the same thing as doing a sigma 2 and then a C3. So we can look at that here. So C3 and then sigma 2 gives us sigma 3. Sigma 2 and then C3 gives us sigma 1. And so these are not interchangeable that way. So it's associative, but it is not commutative. And so this is a non-abelian group. But our C3V does have an identity element, so that's the E, and we see if we act anything on E or have E act on anything, that it just gives us the same thing. That's why this first row and this first column are just a recapitulation of our top and side here, because the E is our identity element, so it always just gives us back the same thing. And we have inverses, and so C3 then C3 bar is just the identity, and that makes sense because if you rotate counterclockwise 120 degrees and then rotate clockwise 120 degrees, you're just going to get back to the same thing you were before. And then so our sigmas here are their own inverses, and that makes sense. If you have your triangle here and you reflect this way and then you reflect back that way, you're just going to get back to the same thing that you had there. And so as we have already seen, which is why I put clearly here, if you read a lot of math books, they like to use things like clearly and obviously a lot. I try to steer away from that, but since we've already done multiple here, we clearly know that we can do multiple of these operations in a row, so more than 2. So we have C3, sigma 1, sigma 3, so we start from the right, so sigma 1 acting on sigma 3. So if we look up at our table, so sigma 1 on sigma 3 gives us this C3 here. And so I have a C3 bar here, so that's actually a mistake. So this should actually be C3, C3, which is C3 bar. So that should actually be C3 bar there. And we can, if we perform the same operation, a single operation multiple times, we can use an exponent like this. So this is the same as C3, C3, which is the same as C3 bar. If we have this, it's C3, 3, C3, C3, which is, so C3 acting on C3, we get C3, C3 bar, which is then just equal to E. And then so if we do a sigma 4 times, since it's its own inverse, we do it, then invert it, then do it, then invert it. And so this will just end up being the identity. But if we do it an odd number of times, so we do it, we invert it, we get the identity, and then we do it again. And so we just end up getting sigma 3. And then so we can compose 2 of these that have exponents on them. And so the first part here, so we have the sigma 1 3 times, so that will be sigma 1, and then the C3 twice will be C3 bar, and then C3 bar on sigma 1. C3 bar and sigma 1 is sigma 3, I think. So let's look up here. So C3 bar on sigma 1, yep, that is sigma 3. So this would just be sigma 3. And so the thing to notice again is that anytime we have this long chain of them, we can always reduce it down to a single element because of that closure. Anytime we do the binary operation with 2 elements of our group, we will always get another element of our group. And so we can look at that here in this example. So we have C3, C3 bar, then sigma 1, sigma 2, sigma 3. So sigma 2 acting on sigma 3 gives us C3 bar. So we would have C3, C3 bar, sigma 1. These last two now become C3 bar. Then if we do sigma 1 on the C3 bar, we get C3, C3 bar. Then the sigma 1 on the C3 bar gives us sigma 2. Then we have the C3 bar acting on sigma 2, so that gives us sigma 1. So we have C3, then sigma 1. Now C3 acting on sigma 1, that gives us sigma 2. And so we've taken this whole thing right here and reduced it down to 1. And we can actually look at this with the triangle. So if we start with our starting triangle, which above I had as 3, 1, and 2 like that, then we first do this one on the far right here, which is sigma 3. So we do a sigma 3, and a sigma 3 is a reflection across there, and so we end up with this, but we now exchange the 2 and 1, so we have 3, we have 1, and we have 2 now. And so then we do the next one, which is the sigma 2, so sigma 2, and so now that is a reflection across this axis, so we interchange the 3 and the 2, so we end up with this. So the 1 stays the same, we now have 3, and we now have 2 there. And so now we do the sigma 1, so continuing down here, the sigma 1, which is a reflection across this, so we're interchanging the 1 and 2. So we end up with this 3, we have 2 up here, then a 1 down there. Now we do the C3 bar. So we do the C3 bar. And so that is a rotation in the clockwise direction. And so the exchange that to there, and that to there. And so we end up with 1, 2, 3 like that. And then we do our last one, which is a C3, and that is just a counterclockwise rotation. So we're just changing all of these things back. And so we end up with a 2, a 1, and a 3. A 3. And so what we can do is we see this, which has the 2 up here, the 3 right here, and the 1 here. That is the same as doing a sigma 2. So a sigma 2, which is just a reflection along this axis here. So if we did this to our original one, we would just interchange the 3 and 1. Well, this one has the 3 and 1 interchange, and so that long line of doing these symmetry transformations is going to just give us something that we can do in a single one because of that closure. Each time we do a symmetry operation on our object twice, that's the same as doing it once, and so you can just reduce everything down to a single operation. And so the elements can also be expressed as products of a subset of elements. And so there is a subset of our set, and we're using the C3V here as our example, from which we can produce all of the other elements of our group. And so, for instance, if we wanted to just use C3 and sigma 1, and obviously this won't work for everything. If you had just the C3 and the C3 bar, that would not be sufficient for a generator because we need at least one reflection. And so, for instance, the C3 bar is just C3 squared. And so we've only used our C3. The E is something we can do either a C3 cubed, or we could do a sigma 1 squared. Both of those will get us to E. So the sigma 2 we can get to from doing a sigma 1 and then a C3, actually C3 squared, and then sigma 3 we can get to from a sigma 1 and just a C3 once. And so we see all of the other members of this group we can get to with just these two members. And so these two members can form a generator for our group. And you could exchange this for any of the other sigmas, and you could exchange this for the C3 bar, and it would still be a generator. But you need at least a C and you need at least one sigma for a generator of this group. And we will look at in future videos more about how you can sort of reduce our groups down in different ways, and in future much more future videos we'll look at generators in a bit more detail. But this is kind of the main idea, the main concept behind a generator is that it is something from which other members of the group can be generated. And one other thing to notice is that we have a cyclic group here, because with our C3, if we do this to any 3 times any integer power like this, we will always get back to E, which makes sense because if you have our triangle here and you rotate it once, twice, 3 times, you will get back to exactly where you were. And you can do that, any number of times, and it will always get you back to where you were. And then same for the sigma. So any of these sigmas, so I'll put an n there. If you do it to the 2n power, you will always get back to E, which makes sense because if you have your triangle here, no matter which one of these axes you choose, if you reflect it once and then reflect it back, you just get right back to where you started. But anyway, I don't want to ramble on too long. I hope you found this video helpful, and I will see you in the next one.